shall pave the way to excellence, they say. Greetings and salutations. I welcome you once again in yet another one-day seminar organized by SUMS, SUMS. Our, we shall discuss a classic invariant of topology, as you've all seen in the posters, and topological spaces known as simplical homology, and look at some other computations. Our speaker for the day is Dr. Kuldeep Saha. We are really honored to have you, sir. He is a postdoctorate researcher from AIATGC Quest, Kolkata. So, we are really honored, sir, to have you in this platform. And without wasting much of our time, I'd like to hand over this platform so we can gain lots of knowledge. Thank you.
Okay, thank you, Shiksha. So first of all, that it was a very generous introduction, and the pleasure is all mine because I think it is always I always enjoy, sharing or just discussing mathematics with friends and also with brothers and sisters like you, so that uh, the it is not important perhaps that whether I'll be able to convey something meaningful today, but I think the whole thing will be whether I can share some piece of mathematics with you, and if you find it interesting, that will be enough for me. Okay, so let's get started. So so I hope all of you can see the screen, right? My the the page I am writing on, you can all see, right?
Yes.
Okay. Okay. So our topic today is what is called like simplicial homology. Okay. I need more precision. So simplicial homology of a CW complex, let me say in general. Okay. So right now, these are like meaningless words to us. We do not know what is simplicial, we do not know what is homology, and also we do not know, what is a CW complex. So let us look at some examples of all such things. So first of all, uh, you know, so let me like the purpose of introducing purpose of an invariant. So this is again a vague term. I am just so what is an invariant? So the purpose of an invariant means that okay, you have say a certain number of objects. Say you have 10 objects given to you, and you have to tell by looking at them, by studying them, whether they are same or not, right? So that is my purpose. For example, in say I give you these 3 objects, a triangle. So triangle, by triangles I mean only hollow triangle. So the interior is not there. Okay. And I give you a square. And I also give you a circle. Okay. And then I give you this thing where, I do not join these 2 vertices. Okay. So now, what is your guess? Can you tell me that how should we distinguish them? All of them has some similarity. Okay. So I need to attach an invariant to each of these objects so that the outcome itself will tell me that, okay, that these 3 among them are actually essentially the same, and this is not same as the other 3, right? So that is the kind of invariant I am talking about. So you can think of it is essentially a function that will eat each object and it will give me some number or something like that. and by looking at the number I will say that this object is not equal to this object. So in particular I'll compute that number for each of these objects, and it is expected that that number will be different. I mean, when computed for this object it will be different from computing for this object, right? So let us try to take, so now I have claimed that this, I have already kind of claiming ahead that these three objects are same in the sense I am talking. So first of all, you can say that, all of them are homeomorphic. All of them are homeomorphic. So what is a homeomorphism? So, so these are like these objects. Now I'll just say the technical term that these are topological objects. So each of these objects are by themselves a topological space, right? So homeomorphism just means that I have a continuous bijection. The inverse is also continuous between all of them, right? From here to here, you have a, continuous bijection with inverse continuous, and from here to here also you have a continuous bijection with the inverse continuous. So essentially I can, just by stretching and pulling, I can convert one of each of them into another. Okay. So this is different. This is my claim. We have not proved yet. So I'll ask one question to all of you, that can you think of an invariant that will distinguish, say, this triangle or this circle from this, from this tree, right? In graph theory, such structures are called tree, right? So from this tree, so say I call this B, and I call this these things A1, A2, and A3. Yeah. So Ujjal, can you tell me that this topological property, A1, A2, A3 has, but B does not have?
Yeah, connected. Means A1, A2, and A3 are connected, but B is not connected.
B is connected.
Uh, it is not a closed figure.
But that is like you have to define what is a closed figure. Yeah, you are on the right direction actually. Essentially, see, that is the intuition. But the one property of the closed figure that you are saying is the following: that so what you said initially is kind of almost the correct answer. That it is, we need to use the connectedness property, because connectedness, compactness, all of these things we have learned in the basic topology course, in general topology course, right? So we'll also try to distinguish in this particular case. So what is the crucial point? That if you remove, say I remove one point from each of this one, and this one, right? If I remove one point from all of this, they remain connected, right? But if I remove one point from here, then this will not remain connected. Does that make sense?
Yes.
Right? So from here, we will get something like this, right? But from here, we'll get something like this. Right? So we are applying the argument of connectivity, but after deleting a point. Okay, so this is very good. So we have been able to apply one of our knowledge from general topology to distinguish these two. But what, say I have a tool that this argument I can use to distinguish between two objects. But then I'll give you another example where it is not so easy to distinguish. For example, this one and this one. So let us call them, say, X and Y. So then how do I distinguish these two objects? So both of them are closed in the sense of Ujjal just said, but yet they are not same. They are not homeomorphic. And we'll see that homeomorphism is a much stronger demand in this case. They fail to be same at a much weaker stage. So Ujjal or anyone else, I mean, what is your guess that how can we distinguish? So can you, so the argument that you applied in this first example, can you modify that to or directly try to apply that in this case? What is the problem? Or is there, I mean, is there no problem? I mean, we can actually find something that will take care of this. Okay, so here is the answer. So see, again from here I can remove one point from here. It is connected. But the point is, I can remove one point from here. I can choose the point arbitrarily, but even then, this remains connected. I cannot guarantee. But if you choose the points carefully, then you will see that it becomes disconnected. If I remove this point, right? This is called the wedge point of two circles. Okay, if I remove this one, then I can distinguish. But it is, here the argument was independent of the choice of point I am removing. But here it is getting involved. Where do I choose the point on my object, right? So the classical notions of connectedness and all that kind of is not very useful. We see that very quickly we run into trouble using only connectedness. Therefore, what we need is
That same problem also lies in first one, because you can also remove the boundary and it will
no
remain connected.
removing the boundary. I won't do that, right? Because I mean you can remove this.
Then there also we should be careful, I think.
Yeah, but it is an obvious choice.
Mhm.
That see the
Yes.
obvious choice is that it is the close you have. If you have a closed object, you have to remove something from the interior. Everything is in the interior. So when you are considering the other one, you have to also take something which is not in the boundary, right?
Huh.
See, we are demanding for homeomorphism, whether there exists a homeomorphism from here to here. So a point on the boundary here can never go to point here, right?
Hmm.
Right. So that
No,
is
no, no. I think we should take map from second space to first space, because
yes,
then we can choose the point carefully.
yes.
Otherwise, if we take from first space to second space, then removing
Mhm.
a point may remove the boundary. So that will be the problem.
Removing a point will remove the. Yes, of course. I'm saying that you can
Hmm.
also do that, but here I will not make that mistake because this is natural to me that if I remove this point,
Yes, yes,
what do I get? I get this,
yes,
which is essentially same as the previous one.
yes,
So I do not get any new information.
yes, yes. But my point is, only we need to uh, take into account from where we should take the map, because otherwise we can run into trouble.
I don't think that is necessary because we are talking about homeomorphism. If there exists a homeomorphism from here to here, there should exist a homeomorphism from here to here also.
Okay. Okay. Thank you.
Okay, so any more questions? Okay, so let us look into our this example again. So now let us take one object from each of these. So say I take this triangle from here and this object B. So A1 and B. Okay, so let us and say I do one thing. I assign numbers. These are just labels. Okay, labels. So do we want to assign different numbers here? Let us start with 1, 2, 3, and 4. Okay. So to each of these, I'll associate some basic object. So for example, see that this object that I have drawn, I can reconstruct this object by using some basic objects. So what are they? They are vertices and edges. Okay, vertices and edges. So vertices are just points, edges are just closed intervals. Right, I mean a line segment joining 2 points in R2 or in any Euclidean space. So each of these objects consists of finitely many vertices and finitely many edges. Okay. So what I will do is first for A1, I will consider this C0 of A1. So what is C0 of A1? It is a finitely generated abelian group that is just generated by one this three symbols. So to not to confuse with the traditional 1, 2, 3, let me write it like this. So what are the objects here? The objects here are the following. This is just a linear combination of points, formal sum, right? This is called formal sum over 1, 2, and 3. Right, so and A1, where A1, A2, A3 lies in Z, the integers, they are integers. Okay, so this is a group. If you see, this is a group because Z is a group, and using that we can define some, I mean, operation additions, and there exist zero element, right, identity element and inverse, all that. So this is an abelian group. Okay, free abelian. So we call this a free abelian group generated by 3 elements. So what are the elements here? So vertices are the elements 1, 2, 3. Okay, so these are my elements. So A1 has vertices 1, 2, 3. Now I'll associate another quantity to A1 which will kind of take care of the edges. So what are the edges? The edges are 1, 2, 2, 3 and 1, 3, say. So now you might say that how should we write them, right? Is there a good way to write? So let us let us choose this writing method that I will always write the smaller numbers first and the bigger number later. In some sense, when I write this edge joining 1 and 2, I will write 1, 2 row. Okay, so in a sense, I am giving a direction from 1 to 2, from a smaller number to a larger number. So 2 to 3 and 1 to 3. So C1A is the free abelian group generated by 1, 2, 2, 3 and 1, 3. Each of them are edges. Okay, so is the definition of this clear? I mean, just instead of 1, 2, 3 here, you take linear combination of these 3 edges. Okay, is that clear, Ujjwal?
Yes, yes.
Okay, so yeah, very good. So now one more thing we want to define. So we want to define a sort of notion of boundary. So what just sometimes ago someone thinking that we have to be careful with boundary. Actually, it's a good point, and you will see that point makes sense because what I will define is a map that I call the one from this C1A1, which is a freely generated abelian group over three edges, to a freely generated abelian group of the vertices. So I will define a map from this group to this group. And note that this group is generated, C1A1 is generated. What are the generators? The edges are the generators. So if I can define it over any arbitrary edge, for example, any arbitrary edge I can write as like this, that I comma j, correct? So where of course our notation or our convention for writing is that j is greater than I. So I have to send this to some element here, right? So I do this. So what is I comma j? For example, if this was I was 1 and j was 2, 1 comma 2. So here is my 1 comma 2, and the boundary map I will write the point, I mean the head of the arrow I will write first, so that is a vertex, minus the tail of the arrow, that is 1. So in particular I will write this j minus I. Okay, and this will give me a group homomorphism between C1A1 and C0A1. Okay, is this map clear to all? Yeah.
Yes, sir.
Am I making sense? So stop me immediately if I talk nonsense, and there is a high chance that I will speak nonsense. Mathematicians do, so there is no nothing to be, I mean, I don't expect decency from you. I only expect that you stop me when I say nonsense. Okay, so delta 1 of so let us write all the maps. So 1, 2 will give me 2 minus 1. So you see that this element, that the image of 1 comma 2 edge under delta 1 is an element in C0A1. Do you see that? Right? So where the coefficients are as following, that minus 1, 1 and 0. Okay? So delta 1 of 2 comma 3 will be 3 minus 2, and delta 1 of what is there else, 1 comma 3 is 3 minus 1. Okay. Okay. So now, oh boy, I think I have to go to next page. But let us finish one computation here. So this is the following, that so now question, does there exist summation, say what should I write, or does there exist, right, C1 1, I mean, so let us give it a name. So sigma 2, sigma 2, not sigma 2, let us call it sigma 1, such that it's a linear combination of 1 2, 2 3 and 1 3. Does there exist a sigma 1 such that delta 1 of sigma 1 equal to 0? That is my question. So we have to solve this equation so that there exists some C1, C2, C3 like this. And I think we can do it directly here. So let us add first the first two edges. So see, now you might ask, how can I do addition? I can do addition because this element 1 comma 2, as am I writing it, this is an element in C1A1. So there is already a group operation of addition is defined. Okay, so I am doing the addition of 1 comma 2 and 2 comma 3 in that group. So that will give me 3 minus 1. And note there is another 3 minus 1. So if I subtract 1 comma 3 from this, I will get 0. So therefore, doing one more step, So 1 comma 2 plus 2 comma 3 and what else? Oh, minus 1 comma 3 gives me 0. Okay. So what is my sigma 1? My sigma 1 is, so answer is yes. And we have computed the sigma 1 to be 1 comma 2 plus 2 comma 3 minus 1 comma 3 such that delta 1 of sigma 1 is 0. Now, what I have done here, I have made the property of closeness explicit. Okay, so Ujjwal was mentioning that, these things are closed, this is not, right? So, when do we call something closed? I mean, so in general, so what I'll define next is the following. So, কোথায় গেল? Next, this.
I have a question.
Yes,
So
please.
is the group structure on C0A1 isomorphic to Z3?
C0?
Is the group structure on C0A1?
Correct. That is true.
Okay.
Yes. So it is, I mean, Z direct sum Z. In that sense, Z. Yes. Exactly. Yeah, that is good point. We should write it down. Okay. So these are just the generators of each of Z, right? Each copies of Z. So what we have found out, see what this is giving. So this is a group homomorphism and delta 1 sigma 1 is 0 and sigma 1 is not 0, right? Sigma 1 we can clearly see this is not a 0. So therefore I have found a non-trivial element in the kernel of delta 1, right? I have found a non-trivial element in the kernel of delta 1 and this is actually there are no other element as a generator in the kernel of delta 1 and that you can see by solving this equation. So you will write delta 1 of say C1 1 comma 2 plus C2 2 comma 3 dot equal to 0 and if you solve it then you will get only this solution. So it is a unique solution C1 C2 C3. So therefore what we have found out here, okay, so but I need to go to next page. So man, what is that? Yeah. Actually, I thought there is a continuous mode in journal where I just need to scroll up and down. I mean, there is no. Just let me. Can any one of you help me? So if you have used journal before, so.
No, I have no idea.
Okay, just a second. Sorry. I want to go to a new. Then again, actually, I have to open a new page. That is the problem. So clear. Okay. What is this? Okay, so no. If I do this, then this page will get, aha. Did it get deleted? Okay, I'll write down the information again, no problem. So what is the
Or
gist?
you can just try Control Z if that.
Yes.
You can undo what you just did.
This one. Okay, control Z. I think it's too late. Anyway, I'll just write it. Yeah. Yeah, I am very poor with these things. Sorry. So, so we defined this C1A1, and then we looked at this map, and we noticed that this was being generated with what was the picture? Let us draw it again. 1, 2, 3. So from lower numbers to higher numbers, that was our convention. So 1 comma 3, 2 comma 3, right? And this was generated by 1, 2, 3, and we found out a linear combination of all these three that we call sigma 1. So in particular, we proved that kernel of sigma 1, kernel of delta 1 is generated by sigma 1, which is a cyclic group, right, isomorphic to Z. Okay, right? That is our conclusion of the previous calculation, right? So this sigma 1 we wrote as like what 1 minus 2. So let 1 comma 2 minus 1 comma 3. So 2 minus 1, 3 minus 1. Therefore, we are left with 2 minus 3. And so if I add 2 comma 3, that will give me element in the kernel. Okay. So now let us look at the other example. So this was A1. So let us look at B now. Okay. So 1, 2, 3, 4. So what is C0 of B now? Tell me. What are the generators? Ujjwal?
Uh, yes, 1, 2,
Yes.
3, 4.
1, 2, 3, 4. Okay. So someone else tell me the generators of C1B. Please.
One,
What are
two,
they?
two, three, three, four.
1, 2, 2, 3, 3, 4. Okay. And we already know what is this map delta 1, right? This map delta 1 can be similarly defined from C1B to C0B. I mean, A1B, these are not important actually, right? So I can define this map by taking any edge I comma j in any space and then send it to just j minus I, right? So under this map, let us write the images of my edges like 1, 2, 2, 3, 3, 4. So what is the image of 1, 2?
2
Yeah, exactly. Yeah, keep on saying, no problem.
yeah.
3 comma 4 will go to 4 minus 3. 4 minus 3. So here also I am faced with a similar job that I have to find what is this group kernel of delta 1 isomorphic to, right? Correct. So I want to see whether a linear combination of all these three edges, no, it has to be a non-trivial linear combination, right? Whether there exists a linear combination such that, I mean, like this, that, plus C3, 3 comma 4, this is 0, right? It's 0 where? 0 in C0B, correct? So let us compute. Okay, so since this is a group homomorphism, right? So these coefficients will, this is like it has all properties of distributiveness and all that. So by using that, I can write this as C1 of delta 1 1 comma 2 plus C2 of delta 1 2 comma 3 plus C3 of delta 1 of 3 comma 4, right? This is from the property of group homomorphism, right? The coefficients will come out, and by distributiveness I can just distribute the delta 1 over sums, over elements of the sum. So then what does it give me? It gives me C1 2 minus 1 plus C2 3 minus 2 and C3 4 minus 3. So let us pair the same things together. For example, what are the coefficients of 1? So the only coefficient of 1 is C1, right? So let us call that minus C1. What is the coefficient of C2? So plus C2, and then it has coefficient, oh, I should have written it other way, sorry. Sorry. Oh, no, sorry. I want to write coefficient of 1, coefficient of 2, coefficient of 3, and coefficient of 4. So that was okay, the previous one. I want to write the coefficient of 2. So what is the coefficient of 2? So here I have C1, and from here I have minus C2 times 2. What is the coefficient of 3? From here I have C2, and from here
Minus C3.
minus C3. C2 minus C3 times 3. And then 4 has only one coefficient, right? C3 times 4 is equal to 0, right? Now see that 1, 2, 3 and 4, these are generators of the freely generated group, abelian group, right? Z to the power 4. So in particular, these are linearly independent elements. As in vector space, if you take a linearly independent element and then you write a linear combination of those elements equal to 0, then all of its coefficient has to vanish, right? That is the definition of linear independence, right? So when we say an abelian group is generated by 4 elements, in this case 1, 2, 3, 4, and then if you write a linear combination of them 1, 2, 3, 4, and you call it 0, then by definition of that this is the generator, so they are linearly independent. So all of their coefficient has to be 0, right? Does that make sense?
Yes.
Yeah. Okay. So we can write C1 equal to 0. We can write C1 minus C2 equal to 0, which means C1 equal to C2, and C2 minus C3 equal to 0. So C2 equal to C3, and C3 itself is 0. So what do we get? So C1 0, C2 is 0, C3 is 0, everything is 0, right? Correct? So all of C1, C2, C3 is 0, right? Therefore, right? So therefore, what is the kernel of delta 1? Right? So there cannot be any non-trivial element in the kernel of delta 1. The kernel of delta 1 is like 0. Am I making sense?
Yeah.
So I wanted to find a non-trivial element. So I started solving this equation. And after solving this, I see that, all my C1, C2, C3 is coming to be 0. So therefore, no non-trivial element in kernel of delta 1. So therefore, kernel of delta 1 is what? As a group?
0.
0. And what did we get previously?
That is isomorphic to Z.
Therefore, we have mathematically rigorously distinguished these two objects. And thereby we have made precise that what is closeness, what is the meaning of cycle, and what is right. So what is the association that we made? I was at the very beginning, I was talking about invariant, that to each object, if you want to distinguish two objects, to each of those objects I want to associate another object. So here the associated object is a abelian group. It is an abelian group, right? So here that abelian group was computed to be Z, and in this case it was computed to be 0. Therefore, I can say since these two groups are different, this object and these objects are different. Okay, does that make sense?
Yes.
Okay, so I am cheating a little bit. So, but let me just state that as a fact that this is indeed. Now you might ask that, okay, for that you need some kind of, you have defined some of, I mean, you have associated number or a group to those objects. But I also have to make sure that when actually two objects are indeed same, and I compute their kernel delta 1 in two different ways. For example, see, this object and these objects are homeomorphic, right? I can write an explicit homeomorphism from here to here. How? Because from this traditional circle, I will write a homeomorphism from here to here, and then I can compose from here to here, or I can directly write. Okay. So in this case, see, here there are 3 vertices, 3 edges, but here there are 4 vertices, 4 edges. So I can compute kernel of delta 1 here using 4 vertices and 4 edges, and here 3 vertices and 3 edges, and here using 4 vertices and 4 edges. So since they are already homeomorphic, this associated abelian group must be same for both of them. It should not depend on the number of vertices or edges, right? So that is the property called invariance of my invariance. So that means when you already know that two objects are same, then they must give you the same abelian group. So fact that if x and y are homeomorphic, so I'll write, two, perhaps what should I write? Not, there is no need to write 2 or something. So x are homeomorphic, and so since we are dealing with only one-dimensional objects, so in particular these are graphs. So let me write x1 and y1. So this will denote their dimension. So our if these are two are homeomorphic, then so kernel of delta 1 for x1 is isomorphic to kernel of delta 1 for y1, right? So this you can prove easily. But what is interesting, okay, so I have to again go to the next page, and I have yet not figured out that how to do it without deleting this. So is that new will oh, what is this? So let me create a new file perhaps. Okay, so but since there is one alibi for me that this is getting recorded. So in the video you can go back and forth probably. Okay, So now let us formally define what I call, the simplicial homology. So our so so our objects of interest is, I will call them, I mean, they already have a name. I will call them CW complexes. Okay. And they have a building block. So it is like it's like constructing a building. So if you construct a concrete building, what are the building blocks? So essentially, the building blocks are bricks and they are glued by using some cement or something. So similarly, some of you must have seen that DIY, do it yourself handcrafts, where you are given some paper pieces like this, okay, and you are instructed that which side to glue to which side, okay, and then you come up with nice figures, like for example, something like this tetrahedron, right. So in a DIY, if I am given say 4 such pieces, okay, 2-dimensional triangles, and I am said that, okay, glue this side to this side, this side to this side, and then finally you can construct something like this, right? So CW complexes are essentially all the elements. So for example, the case 1, let me start with 2-dimensional CW complex. 2-dimensional CW complex. And I think for in this talk, I will only talk about up to dimension 2, because the generalization in higher case is just straightforward and there is nothing new to it, nothing more to it. So 2-dimensional CW complex, so basic building blocks, right? Blocks. So in DIY, maybe that you are only given this triangular like pieces, but I can be more refined so that I just give you for some say button like things, which are my vertices, okay, and then I also give you say how many, 1 2 3 4 5 6 edges, like this. How many? Yeah. And then in addition to this, I give you this four triangular faces. And then you can start from the scratch, that first you take care of, you just place this, 4 things in space. So they are called zero simplices. So simplex is singular, simplices is the plural, and so zero simplex is just a point. Okay. One simplex is just a copy of this. When I say copy, it is up to homomorphism, homomorphic copy of this line. Okay. So these are closed, please note. And 2 simplex is a triangle. Okay. So these are my building blocks for a two-dimensional CW complex. And believe me, you can construct very pathological examples of CW complexes just by using these 3 kind of simplices. One might think that the number of example must be very restricted. It is not. It is not. Okay. So what do I do? First, I join. So I attach, say, this edge. So what? Say I attach this edge here, I am just reconstructing this figure. So this is used. Now this I am attaching here. This is used. This I am attaching here. That is also used. And say this I am attaching here. Okay. So I have two left with. So I'll attach here. I am left with one. And then what I'll do, I have four two-dimensional simplices. So, and each of them, say the first one I will attach here. So I will fill up the first face here. Okay. And then glue the second one like this. And similarly, the other two also, which lie on the other side. So it obstructs my vision, but I hope in the picture you get the idea what we are doing. Some other examples of the say now I can go on doing this. So I can always start with a graph. I can always start with a graph, and I can go on doing this. So for example, so these are my zero simplices and these are my one simplices. Okay. And now I want to attach a two simplex. So note that here I can attach two simplex because the boundary of my two simplex, which is a triangle, is same as union of three edges. But here I also have a hollow region. I have a cycle here, but here I cannot attach a two simplex. Okay, is that clear? I mean, it is allowed to attach a two simplex here and here, but here I cannot do that. I could have done that if there was an edge between these two vertices. Then I could attach one two simplex here and another two simplex here. Okay, but in general, I am not allowed to do that. Okay, so are there any questions till this point? Am I making sense? Am I making sense?
Yes. Yes.
Okay, so and another example, say if you want to see some more visually interesting examples, so consider this. So my point is, right now you have been thinking, okay, everything looks like one graph and two manifold, which are partially two manifold and union of graph. They are only examples, but it is not. For example, there can be more complicated. These are not complicated, but once we for if you are not like if you have never seen them before, it might look. But we can usually visualize these objects in our daily life, right? I can take such pieces of paper like this and construct these things, right, by hand. So this is an example of another two-dimensional CW complex. So if you take a point here, you can go along this plane, or you can go along this plane, or you have a choice to go along this plane. So these are definitely not manifold, because a two-dimensional manifold has any point in the manifold, the neighborhood looks like R2, two plane. But here we see that if you take any point on this line, it is not like that, right? It does not look like R2. So, yeah. So, for two-dimensional CW complex, again, we can play the same game, right? So, say what is our game now? Our game is that instead of constructing C0, C1, I can also define, right? So if I have X2, a two-dimensional CW complex, I can define C1 of X with say finitely many. So let us just look at this example. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we give arrows. And right, we remember the rules, don't we? So I can give arrows. So C0x starting from 1, 2, dot, 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 10. C1x again, right, 1, 2, 1, 3, 2, 3, 4, 5, 3, 5. Okay, so let us write all of them just to be clear once and for all. Perhaps I will not write again. So 6, 7. Have we finished all of them? I guess so. Okay. And C2x. So C2x are just, you have to write the two-dimensional complexes with three vertices they have. So just write the points in order, right? So 1, 2, 3 from lower number to higher number. That is my convention now. So one is here, another is here. So this is 8, 9, 10. Right? And again, so delta 1 we already know. And what about delta 2? You might ask, right? What about delta 2? How do you define delta 2? So let me give the description of delta 2 in general. So C2x, so that, I mean, for any, not for this particular example, for any example, you can write it yourself. Okay, so Ujjwal, I have a question. So can I go on till 8:30 or I have to stop before?
Yeah, you can like take your time. Yes.
Okay, thank you. Okay. So, yeah. Okay, so let me define it like this. So say the three vertices, so 1, 2, 3, 1, 2, 3 are the level of, say the level of vertices are now V0, V1 and V2. Okay. Then I will define the map like this. So what is the way that first you remove V0. So then after removing V0, so see, this is a map from C2x to C1x. So in the image should lie in C1x. So image should be a linear combination in these edges, right? So first remove V0 and write V1 comma V2. And then next remove V1. Okay, we have to take care of the sign, alternate sign. So start with plus. Okay, and then the next one you remove V1. So you are left with V0 and V2. And then again alternate your sign, plus remove V2. So you are left with V0 and V1. So this is my map. So now some of you have already guessed that in general what should I do? So this is a remark, I am not going into detail, that in general, an n simplex is a convex hull of n plus 1 points in R n plus 1. So in general, a sigma n, if it is a n simplex, I can write it as V0, V1, dot, 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 Vn. So now you might ask that why are you talking about convex hull and all that? Because it is the natural choice. For example, so let us see that our notion of one simplex and two simplex whether coincides with this. See, our notion of one simplex will mean that a one simplex is a convex hull in case of dimension 1 is just the line segment joining 2 points in R2, n plus 1, n is 1. Okay. And for two simplex, it is 2 plus 1, so we have to be in R3, and if you join these 3 points 1 0 0 0 1 0 and 0 0 1, then the convex hull uh, of 3 point is just the unique two-dimensional plane segment that passes through these 3 points, right? Is that clear? Does that make sense? So in general, any n simplex is like that. I mean, you just take those one. So for example, if I go one dimension ahead, so 1 0 0 and like 0 1 0 0 and 0 0 1 0 and 0 0 0 1. So these are coordinates in R4. So you have 4 points in R4 and you take the convex hull, and that will give you the tetrahedron. That is the three-dimensional simplex, right? So I'm not drawing this in R4 because we cannot see R4 with our eyes. Okay. So, but in fortunately, at least this one we can draw inside R3. But nonetheless, this definition generalizes to all dimension. For example, how will you write it in general dimension? So delta. So 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 just mark this, remember this. So there is a pattern, it is easy to remember that first plus you remove the initial term, then minus you remove the next term, then plus you remove the last term. Okay, that is my boundary map. And I wish.
Sir, you can try Control D.
Control D. Okay, let me. Ah, thank you, man. Thank you.
I have little doubt.
Yes,
Like
yes.
I didn't understand what is your definition of CW complex. How you are defining?
How am I? Okay, so I am defining a two-dimensional. So for our purpose, we are only concentrating on two-dimensional CW complex. We can define it for n dimension.
Mm.
Okay, so the dimension is
This is this
yes,
is
yes.
the definition of simplicial complex, not CW complex. That is general. I think.
That is general, but CW complexes, simplicial complexes are also
Like
CW complex.
RP1. No, RP1 is not a simplicial complex, but it is a CW complex, cell complex.
What
We
do you
cannot
mean
do
by RP1 is not
uh,
simplicial
real
complex, right?
projective space. It is not a simplicial complex, but it is a CW complex.
No, it
So
is
I
not.
think you
RP1 is
no,
homeomorphic to S1, and if you can
no.
give a
It
simply
is not homeomorphic to S1.
RP1 is
Uh,
homeomorphic to S1.
no, no. You have to also attach the antipodal point over there.
See, I do
It's
not
not
want
bound.
to go into futile arguments here. RP1 is homeomorphic to S1. I mean, there is no two way
No,
about
no.
it. I think we can discuss it later if you want to discuss that. I mean,
Okay.
okay. I
Okay,
mean,
no,
there is
no,
no
that
point
same
in this.
problem that happens to us in like in our coursework. That Lee book also
Yes,
has this statement that RP1 is homeomorphic to S1, but
yes.
that is little troublesome because we have to also attach antipodal point.
Yeah. So, do you want to see a proof of
Mm,
RP1 homeomorphic to S1 right now? It takes 30 seconds.
yes,
Yeah, I should give it because
yes.
it is very easy to show. So no point to, on arguing over it. Okay. So what is the definition of RP1 or RPN in general? So let me. So first define SN. Okay. So SN is collection of all elements in Rn plus 1 such that x1 square, x2 square is equal to 1. Okay. That we call this the standard n-dimensional sphere. So in
Mm,
particular, S1 is just, I mean,
X1,
you
X2.
know, right? So
Yes.
just, okay. Now what you do? So here you have S1 sitting inside R2. So and if you have a point on S1 that I call x1 comma x2, then an antipodal point of this is just minus x1 and minus x2,
minus. Mm,
right? Okay.
mm,
Now, in general, here also, in general, over Sn, the antipode, so so if I take x1, x2 dot xn or xn plus 1, the antipode is just minus of this, all of it is the exact opposite point with
mm,
respect to the origin. Okay. Now, RPN is defined as a quotient space of Sn. So, what is the quotient? So, you take Sn and then you identify. So, what you do, you take these 2 points x1, x2, x3, and xn plus 1 up to and its antipode, and you send them to a same point. So, x1 x2 dot xn plus 1, this is identified. Identified means that by hand you can just glue those 2 points. Okay, you can use a kind of glue and just declare that these 2 points are the same. So minus x1 minus x2 dot minus xn plus 1. Now, okay, so now the thing is the following. So for what is the case of RP1? So RP1 is similarly just this. So therefore in the picture, let us try to understand it. So we have S1 and we have to find a quotient space, that is RP1, by attaching antipodal points to a same point, right? So now there is a unique, I mean, you can do it by hand. So how do I do? First, I remove this point, which is minus 1,0, and this point 1,0. So now note that these 2 points are antipodes. Okay. So once I have removed this, I have an open arc above, I have an open arc below. And now each point here in the open arc is identified with a point here. Correct? For example, this point here will get identified here, and this point here will get identified here. So now I can just take this with my bare hand and I can rotate this and glue these 2 line segments, 2 open segments, essentially to get 1 open segment. Does that make sense? I can do this antipodal gluing. Once I have to remove, see, I cannot do it by keeping S1 intact. But once I remove minus 1,0 and 1,0, I can actually take this segment and rotate it and then match this portion to this portion, this portion to this portion, and this portion to this portion. And I get this one. Okay? But under the quotient map, minus 1,0 and 1,0 again will give me only one remaining point. Right? Because these 2 points are identified inside RP1. So what is the only possible case of my quotient space? That these 2 open sections has to be compactified using this 1 point. Therefore, you get a copy of S1. There is no other way.
okay. But actually, there is some problem with this. But I don't want to go in that
Yes, what is
because
the problem?
I
No,
will
see,
just say, like, if you
I'm
take,
not saying that you are wrong, but I mean, you have to like pinpoint a question, right? That this is what
yes,
I have problem
yes,
with. Yeah.
actually, the problem with this is like I don't know I should go there or not, but if you compute the fundamental group of RP1, that is
Yes,
Z
yes,
mod
that is Z.
2Z,
That
and
is no,
fundamental group of
no,
no, no,
no, no.
Z mod 2Z, right?
RP1 is Z.
RP1
I
is
think
S1.
RP1 is
I have
isomorphic to
Yes,
S1.
so
How can it be
RP1
have?
का फंडामेंटल ग्रुप इज जेड ही होगा.
हाँ, अरे अगर दो चीज होम्योमॉर्फिक है, if two things are
no,
homeomorphic, the fundamental group has to be same. I
no,
just proved that
I'm sorry. I'm sorry. I think I am wrong over here. What I am
what
saying.
you are saying is RP2.
R,
RP2 is Z mod,
RP2 is
and in general, pi
S1,
one
right?
RPN is Z mod
Z mod
2
2Z.
for all n greater than
And
equal to 2.
and what will be the? It will not be isomorphic to S2. That means homeomorphic to S2.
RP2 is not homeomorphic to S2 because pi 1 S2 is 0.
Okay.
Fundamental group
I think I am
distinguishes them.
wrong over here. Yes.
In fact, in
Yes.
general, RPN is not same
Okay.
as
Thank you.
Sn for all n not equal
Hmm.
to 1. Yeah.
Hmm.
So, okay.
Okay.
So, where
And
were we? Yes.
CW complex and simplicial complex are also same. Hmm.
No, I have never said that CW
Thank you.
complex, simplicial complex are same. But every simplicial complex is same as a
No, no.
CW complex. I mean, it
It
is
will be
a,
a CW complex. Yes.
yes, yes, right, right.
Yes.
So,
Thank you.
okay, so yeah. So, uh, okay. So we see that we have defined this boundary map from C2x to C1x, and in general, also we can define it from Cn plus 1x to Cnx. Okay, so that's what I wanted to say, but I think I'll not go into that because my object in this discussion is to compute some explicit hand-on example. See, uh, although this is a personal point, but my experience in doing topology or in mathematics in general is the following: that if I mean in our courses and all that, we are spoon-fed lot of technical terms, definitions. This is called this, that is called that, logical proof. Okay, that is a part of mathematics, of course, but that is not the fun part. I mean, that is a corollary to the fun part of mathematics. And the fun part of mathematics, in my mind, is like hand-on experiments with your objects. So you must have concrete objects, whether it is algebraic or geometric or topological in nature. We must first understand concrete examples. Then that general theory and general definitions will make sense. But if we kind of at the very beginning we get hold of only theory and forget examples and don't go into various problem solvings, uh, mathematics will soon become boring to you. That is my understanding. So therefore, I chose to do computations today, no theory. Okay, but of course we are building the theory via our examples. Okay, so delta 2 is defined. Okay, so this much, up to this much, do you have any question? Because now next I'll go into, I will go into the next step. Do you have any other questions? Anyone? Can I go? Can I go to the next one?
Yes.
Okay. Yeah, so Control T. Yeah, thanks, man.
Sure.
It saved my day. So, yeah, so now what do we have? We have C2x. From there, we have a boundary map delta 2 to C1x. And from C1x, we have a boundary map to C0x. Okay, now here things gets interesting. So my claim, so I can compose these two maps to go from C2x to C0x, right? My claim is that C1 composed with C2 is actually 0. 0 in C0x. So, and I think it's, you can prove it just by hand. So let us do that. Okay. So how do we do it? Good. So we have to take an element here, and then so we have to show. So need to show. Need to show that for any sigma 2 in C2x, this map is 0. If we can show that for any sigma 2 this is 0, then we can show this claim, and that is the definition of this thing. So now note that I can write sigma 2. I can always write sigma 2 as some linear combination of two simplices, right? So therefore it will look like, say, what should I write? So Vi0, Vi1, Vi2, and then as I varies, this three vertices will change to give me new two simplices, right? So now what we will show is that, in fact, I do not have to take any linear combination. So in particular, the generators, if I can show that for the generators this equality holds, then I am done, right? Then for any linear combination, this will hold. Okay. So let us take any arbitrary generator. So let us V0, V1, and V2, and apply delta 1 plus delta 2. So this is same as delta 1 being applied on this delta 2 of V0, V1, V2. Okay, so quickly tell me what is this map? What is the image of this map? Ujjal, bolo.
Delta 1.
Hello?
V0 V1 plus V1 V2 minus V0 V2.
Hold on. So V0. Yeah, can you just repeat it?
V0 V1
V0 V1
plus V1 V2
plus V1 V2, good.
minus V0 V2.
Minus
V0 V2.
Right. Yeah. So this is correct answer, but just to be consistent with our convention, you see that this coincides with our convention, that first remove V0 with positive sign, so that we left plus V1 V2, which is here. Then remove V1 but change sign, which is here, and then remove V2 but again positive, which is here. Very good. And now by distributiveness we know that this is same as V0, V1, V2 minus delta 1, V0, V2. So what are these images? Right? Huh? So
Yes, sir.
Please note whether I make error in the computation. So अभी देखो कि this gets cancelled, ये cancel हो रहा है, and this is also getting cancelled, so we get 0. Okay. Does that make sense?
Yes.
Okay, good. So now what does that mean? That means that if I take an element, so if my say tau 1, so one dimensional, so any elements in C2x is called a two chain. Elements in C2x are called two chains, and this is called two chain group. Any element in C1x is called one chain, and so on in any dimension. So in C and X, an n chain is just a linear combination of n dimensional simplices. Okay, so if I take a one chain that lies in the image of delta 2. So image delta 2 is again a group, right? Again a subgroup of what? Again a subgroup of C1, right? C1x, correct? Right, recall that C2 was from C2, delta 2 was from C2x to C1x. So the image of delta 2 is again a subgroup of C1x, right? So if I take a one chain inside that subgroup, then delta 1 of tau 1 is always 0, right? That is what we have shown here, correct? In particular, image of delta 2 always is contained in the kernel of delta 1. Does that make sense? Okay. Okay. So what do? What is, I mean, the intuition behind defining all this? So, kernel of delta 1 is essentially computing what? The cycles, one-dimensional cycles. Like this is like collection of one-dimensional cycles. Okay. Now, but I am saying that just counting kernel of delta 1 is not enough, because I want to compute the essential one-dimensional cycles. For example, say in this example, I take this CW complex or simplicial complex where I have 4 0 cells, 5 1 cells, 5 1 simplices, and only one two-dimensional simplex. Okay. Now note that 4. So note that this thing, what is the boundary of this? This minus 3 plus is this? This is 2 3 minus 1 3. Right? I mean, so if I trace here, that you're going along 2 3, and then you're going this direction. In the other direction 1 3, and you are going in the same direction as 1 2. So this is actually a what? So this is delta 2, and if you see that this thing is actually an element in the kernel of delta 1, right? So delta 1 of this object is 0. That is what we have shown, because delta 1 composed delta 2 is 0, right? Delta 2 of this object is 0. So this is a one cycle, right? This 1 2 1 2 plus 2 3 minus 1 3 is a one cycle, and also this is also in one cycle. See 2 4, I think, okay, so 2 3 4 is our thing, and okay, so this is minus plus 2 3 and plus 3 4. So this is also one cycle, this is also one cycle, but there is a important difference between these two cycle, one cycle. See, this object is already bounding a two-dimensional CW complex. Okay, so it is in some sense it is not essential, although it is a cycle, but I can get rid of this cycle if I want to, right? So how do I get rid of this cycle? Because it is bounding already. So a cycle means a one-dimensional hole. Okay, so perhaps in popular terminology, you have heard that homology counts holes in a manifold or in a simplicial complex. I think Wikipedia page also says that, but it does not only count holes, one-dimensional holes, but it will count holes only when they are significant, they are essential, because I have captured a hole 1 2 3 here because this is a closed path, but that hole is now filled by this two-dimensional CW complex, so that should not matter to me now, right? So that is what we are doing when we are looking at the image of del 2 inside kernel delta 1. So now look at the other example, minus 2 comma 4, 2 comma 3 and 3 comma 4, this one. This on the other hand is a one cycle, and it is an essential one cycle because it does not bound a two-dimensional simplex, right? So therefore, let us define the first homology group. So H1 of X is defined as the quotient group kernel of delta 1. So I will collect all the one-dimensional cycles, and then I will kill those one-dimensional cycles or combination of those one-dimensional cycles which does not matter. And what are those? Which lie in the image of delta 2. So this is the essential information about one-dimensional holes that I extract from my space X. Does that make sense? Am I making sense?
Yes, sir.
Okay. So now you might ask that, well, in our first example that we computed, this one and this one, you only computed kernel of delta 1. Where is image of delta 2? Well, in our first examples, there were no two-dimensional simplex, right? So C2 was zero, C2 of this A1, this was named A1, C2 of A1 was zero group, right? Because C2 has generators, only two-dimensional simplices, but there were no two-dimensional simplices. So C2 is 0. And also C2 of B was 0. Therefore, the image of del 2 was already 0. So in our previous case, H1x was same as kernel of delta 1. We had nothing to kill. Right? So actually we have already computed the H1 of this and H1 of this. And we see that this is Z and this is 0. See, it is clearly, I mean, our intuition, we have just made our intuition mathematically rigorous. That's all. That's all, right? So here I see a hole. Here I don't see a hole. That's all. But to just make it mathematically rigorous, we had to go through this, setup in some sense. Combinatorial setup. Okay. So I would like to compute at least some examples. So, but okay. So now I think I should say something about the point of that. What is the difference between a simplicial complex and a CW complex or a delta complex? So control T, yes. So, for example, a two simplicial complex and a two CW complex. So what is a two simplicial complex? So a two simplicial complex is again the building, as I say, they are zero dimension, I mean zero simplex, one simplex, and two simplex. You can have finitely many of them, and you are allowed to glue them, but the gluing condition is a bit restrictive. So it is like saying that, say inside R3 I want to glue my pieces. I have points, I have edges. I mean the edges are rigid. I mean you can think of the edges as like this pen, and they are rigid objects. You cannot bend them or twist them. And the two faces are again like made of hard cardboard, like triangles. You cannot bend them and twist them. And again, you just play the game of do-it-yourself cardboard, by making Lego figures, by gluing those two things. And during gluing, you are not allowed to bend or twist them, right? That is the condition of gluing. And you can glue them by their common faces. You can glue them by their common faces. Okay, so that is two simplicial complex. Now, uh, so what I will do, I will take a topological space S2, the two-dimensional sphere, which usually we draw it like this, like this, the surface of the Earth. So this thing, this picture that I have drawn, is a simplicial complex structure on S2. Okay, now I will draw a CW complex structure on S2 that is not a simplicial complex structure. For example, so now how do I define? So already I have we have showed that it is like only about the building blocks and how the recipe, that how to glue each block. That is all we need to construct a space. So here also I will take this rectangular or square sheet and I will build my sphere starting from here. And so what I need to tell you, I need to tell you how to glue which side to which side. Okay, and that I will define by labeling. So I will glue this edge with this edge with the direction. Okay, and I will glue this edge with. Okay, so now note that if I divide the in between space by using the diagonal, then this region is again homeomorphic to a two-dimensional simplex. This region is again homeomorphic to a two-dimensional simplex prior to gluing, right? But now note that if you glue like this, you have to, there is no option, you have to bend the faces F1 and F2, right? If I do not bend the faces, then what I will get? I will just get a flat triangle again. But if you do not, you are allowed to bend F1 and F2 like this. So what we are doing is this flat triangle, but then again you can construct something like this, right? Something like this. Okay. So now these lines are now carved. I do not know whether this picture makes sense, but right, like it is like, say this is a rubbery material that we have taken, and then I poke this with some stick and this will become bent, right? Okay, so it is same as like the difference between a disk and the upper hemisphere of the earth. They are same, but here I am allowed to bend, but here I am not allowed to bend. Okay, so simplicial complexes, the gluing is such that I cannot allow any bending of the building blocks, but here I am allowed to bend the building blocks of my simplices. So therefore, is it clear that this space as the identification? So I do nothing in the interior. There are no identification in the interior. The only identification is on the boundary. I glue this to this and this to this. So if I glue the first step, then what I get something like this. Okay, and so what do I get? Yeah, I think I will get this. Is this picture making sense? Like, Ujjal? Is the picture making sense? So if I glue the first step, I get this, and then I will. It is. I see. I personally use the terminology sewing. Okay, इस portion को इस portion से we have to sew it. Think of this as a fabric material, and this portion to this portion. Then what you get is a copy of. Because sewing seems more natural to me in this case. So this is a hollow thing, you see. And this is, you can see that this is same as S2, right? So this that I have drawn on the right hand side is a CW complex structure on S2. That is not same as the, that is not a simplicial structure on S2. Because here I am bending. When I am gluing, I am allowed to bend my two-dimensional simplices. But up to homeomorphism, both of them are same. There is absolutely no problem. But the one caveat, see here, when you are not allowed to bend, then there is an interesting question of combinatorial nature that say, I give you S2. What is the minimum number of two simplices you need to give a simplicial complex structure on S2? Right? So you see that this is the minimum we require. There must be at least 4 faces to give a simplicial complex structure on S2. Whereas a CW complex structure on S2 can have as low as only 2 faces, 2 simplexes, right? So I hope I have given some idea about two simplicial complex and CW complex. Okay. So so do I have time to do one more on last computation? I want to compute the homology of S2 using this CW complex structure, or should I leave it as an exercise to you? Since it's late, so yeah. Ujjal?
Yeah, we'll try by ourselves.
Okay, yeah. Okay, so exercise perhaps. See, I mean, let me just write it clearly that, so what the space, so I do not know whether this is S2. Now I know, but initially one would ask you just by this description that I have a rectangular sheet, rubber sheet, and you are identifying, this side with this side and this side with this side. So what is the simplicial homology or CW homology of this space? So first triangulate the space. So see this, if you call this side A, then all this side is already named A because they are identified. If you call this side B, this side is already named B because they are identified. But I need to break the space into triangles, and the intermediate edge, I call it C. Okay, now note that I am gluing this side to this side. So if this vertex is V, then this vertex is also V. Okay, and these two vertices I will give different names, W1 and W2. And for the faces, let us give name F1 and F2. Then from here, my C0 of X is V, W1, W2. I just want to kind of give some information so that you can do the rest of it at home. So A, B, and C, and C2X is generated by F1 and F2. Now you might ask, Kuldeep, you are cheating. So you gave us numbers like 1, 2, 2, 3, and then suddenly you are jumping into other notations. Okay, you can also write A as W2 comma V, B as W1 V, W1 comma V, but I am not writing it here for brevity purpose. Okay, that is the reason. And so what you have to find again, like you have to compute like delta 2 of FIs for I1, 2, and again like delta 1 of A and B. Okay, so that's how, and you know what you have to do. So, oh, by the way, I forgot to mention H0x. So what is H0x? So H0x is again just kernel of delta 0. So I mean H0x is just the number of kernel of delta 0 divided by image of delta 1. So you have to see that whether there are identification relations between V or W1 and W1, W2, right? So this will be some group generated by V, W1, W2, quotiented by some relation among this, which will come from boundary map of C1x from, and H1 and H2 are defined similarly. Yeah. Yeah, I think we should stop here. It's already late. Yeah, sorry, I stretched it this far. Thank you.
Hello.
Yeah. So, any questions? If you do, you have any questions?
So I think there are no questions.
Okay. See you then.
Uh, 1 minute.
Yes.
Kuldeep,
Yes.
you say kernel, if two space are homeomorphic, then kernel should be same.
If not any two space, if two spaces are graphs.
Oh, for graphs, the kernel are same, and for other space, we need
H1.
to
H1 is
see
same.
the
If
H1 is
in
same.
fact, I mean, if two spaces are homeomorphic, all of the homology groups
Mhm.
will be same. H1, H2, and whatever there is.
Yeah. And I want to ask you, since you are a topologist, so is there any reference to learn about Poincare spheres?
Poincare
Poincare
homology
three
spheres.
spheres? Yes,
Poincare
homology spheres.
homology spheres. You will find about homology spheres. So I'll tell you how I learned first.
Mhm.
So if you do you have the book of Hatcher's algebraic topology?
Yes, I have that book,
Yeah.
but I didn't find
Okay. So yeah, I mean, if you
it
go through it, you will
in
see that. So first of all, in the chapter of fundamental group, that is chapter 1,
first two chapters.
fundamental group, you will see that there is mention of one
Mhm.
space that
Yes.
is called, I think, acyclic or something like that. So there is one example of, I mean, it is only mentioned that this is known as Poincare homology group, and but then in the next
Mm.
section, in the next chapter, chapter 2, Hatcher recalls that examples, and so in the first section, fundamental group, he computes pi1 of that space.
Okay.
And in the
Mm.
homology chapter, he computes the h1 of that space. And then he says that, see, the
Okay.
h1 is 0, okay,
Mm.
and but the pi1 was not 0, that he computed previously. And
Mm.
there I think he mentions that it is homology. These are examples of uh, three-dimensional homology spheres, which were first given by Poincare himself. That is one
Yes.
source. Another source
Uh,
is, if you find any book on three-dimensional manifolds, knot theory or
okay.
three-dimensional manifolds. So one book is by Rolfsen, Del Rolfsen, Knots and Links. There you can find
Okay.
it. Another very good book
Okay.
is by what is his name? V. Prasolov. If you have that, it's a translations in
Mm.
mathematics by AMS. It's translation of a Russian book written
Okay.
by V. Prasolov, and there is, I think, Prasolov and Sozinski, I think, the name of the two authors. And there
Mm.
is another good book by Nikolai Saveliev. The name I'm forgetting the name of the book. It's like something three manifolds and Casson invariant, something like that. But Rolfsen is easily available on the internet, and there you can find all of this. Dale Rolfsen's Knots and Links.
Okay. Okay. If you can send the link of that page only, then it will be nice.
Yeah, I can send you
Screenshot of it.
the. I can send you a PDF. I have a soft copy. I can
Oh,
share
okay.
that.
Okay. Thank you.
Thank you. Welcome.
So exam, maybe like we have to like end the session formally.
Sure. Yeah. Bye. See you.
So I'm immensely thankful to you, Dr. Kuldeep Shah, for your valuable time.
Yeah. Yeah. My,
Today's session was without a doubt a massive success. I also thank all the audiences. Today was a tremendous session, and we shall anticipate for such surpassing events in our upcoming days. The topics which we've discussed are absolutely beneficial to us, and we have sent a link in the chat box. It is a feedback form, so we can it would be it would be very beneficial for us if you just fill up the form and let us know your feedback. Thank you.
Okay. Bye, Ujjwal.
Bye bye, Kuljita. Thank you so much.